Hello. Hello. Yeah. So, hello everyone. Welcome to the ninth tutorial of our course Introduction to Classical Mechanics. So, in the last class, some of the students told that they are facing some problem in solving the assignments. So, today I thought I will go through some of the problems of your past assignments. Mainly, I will cover assignment number 5, 6, 7 and 8 in this video. I mean, I will cover some of the problems, not all the problems. So, if you have any other, if you face any problem with other problems which I will not solve today, so please let me know. Okay, and you can mail me in my email ID and I will go through those problems as well. Okay, so let us start. Just a second. Yeah. Okay, so yeah, so the first problem I will do this one. So it is now I think you can see the questions. So I have given you some hints to how to solve this problem already in my previous video, but I will do it today again, if you so that you can understand it more clearly, I mean in a clear way. So the problem is a one dimensional system that is oscillating around the equilibrium position, which is given as u equals to a q to the power 4. So let me, so I have solved the equation so that I can go through step by step and that will save some time. Okay, so the given potential is a q to the power 4, where a means alpha is greater than 0, and T, capital T, is the time period of the system when it has an energy of capital E. Then upon increasing the energy to E, what will be the time period? So we have to find the time period. Okay. Okay. So the total energy equation says that your kinetic energy plus potential energy equals to total energy. So this is the kinetic term, this is the potential term, and that is E. Capital E is the total energy, which is a constant. Now if you follow this procedure, then you can reach to this particular equation, which tells you that q dot, which is the equation of q dot, that is dq dt. Here q is the q is acting as the I mean spatial coordinate. I mean you can think q as r. So dq dt, you will get this, and now we will integrate this expression from 0 to t. So here small t is the time which it takes from its from going its I mean center. So a q to the power 4 potential will be like this. So the particle at t equals to 0 is here, and it will go at the highest position with energy E at a time t. So that's why we are doing the integration from 0 to t, and similarly your potential is given, and at the highest position your kinetic energy will be 0 and all the energy will be in potential energy. So your V is equals to E, which is a q to the power 4 at q equals to q max. So from there you can calculate your q max, and that will be your upper limit of the q integration, which is coming here. Okay, so your q max is E by a to the power 1 by 4th, and it is 0 at the equilibrium position at O, say. So this will give you the time period of the system. Now following this method, if you calculate, so I have written it small t. So because the total time period, which is capital T, it is actually 4 times of the small t, because the problem has a symmetry and the time it takes from going 0 to say a, that is the highest position. So 4 times of the time which is takes from going 0 to a is actually your time period. So capital T is proportional to small t. It is just 4 times of the small t. That's why I have used small t. You can use you can multiply it with 4 also and use at capital T. No matter in that. So if you do this integration, now the main tricky part of the solution is this one. So this is, you can understand from is, I have just put VQ is equals to AQ to the power 4, which is given in the equation. Now what we are doing is we are taking the e to the power half term common from the bracket. So then the second term will look like this, a q to the power 4 by e, and we are telling that a q to the power 4 by e as x. So it is called the scaling procedure. So we are substituting the a q to the power 4 by e as x, and if we substitute it in a proper way, just go through the lines which I have written, that is a by e is constant and 4q cube dq is equals to dx. So from there you can calculate the dq, which will be this, and just substitute this dq in this equation. Okay, and all the other terms just substitute it in terms of x, so that our target is to convert our integration from q to x. Okay. So by substituting this, we will get this equation, where you can see that it is here is the x dependent part, here is the x dependent part, and all the other part, that is capital E by a, or this term in the denominator, these are constant. I mean that capital E and a all are constant. Okay, so I have used by mistake I have used a instead of alpha, so just consider it as a and alpha as same actually. So you can take your e to e by alpha, e by a term outside of your integration. Okay, so now if you do that, so this term comes out of the integration, and your integration is purely on x, and properly I have used the upper limit and lower limit of x. Just use this equation, a q to the power 4 by e equals to x. From here, by substituting your q max and q min, you can find x max and x min. So that will come out as x max equals to 1 and x min equals to 0. Now this integration will give us some value. I mean we are not and this is not depending on the e. Okay, so this integration will give us some value. We are not interested in that. Some value will be there. That's why I have used the proportional sign, not the equal sign. Okay, so actually we want to find how our t is depending on capital E. So if you want to focus on this particular thing, then you can see your, if you calculate this e and this e properly, then you will find that t is proportional to e to the power minus 1 by 4. Okay, proportional to. Now that is our main result, that t is proportional to e to the power minus 1 by 4. So now coming to the question, it is asked that if our total energy change from capital E to capital E, then what will be the change in the time period. Okay, so I have written that for E my time period is t1, and for 2E my time period is t2. So from this equation, t1 by t2 equals to E by 2E to the power minus 1 by 4th, and if you calculate that, you will be cancel out. So 1 by 2 to the power minus 1 by 4th. So your final result will be this one, that t2 is t1 by 2 to the power 1 by 4th. Okay, that means t2 is the new time period, which is corresponding to 2E energy. So if the energy increases by 2, I mean than the previous energy, 2 times than the previous energy, then your time period will decrease by a factor of 2 to the power 1 by 4th. Okay, from your initial time period, which was t1. So your new time period is 2 to the power 1 by 4th, times less than the previous time period. Okay, so this is our result, and generally you can write it as also, if your potential is V is a q to the power n, I mean for our case n was 4, so n is generalization, then your t2 will take the form t1 by 2 to the power 1 by n. Okay, just I have substituted my 4 with n to get the generalization. I mean if your potential is in following up exponential form with the power law n, then by changing your energy from E to 2E, you are getting a decrement of your time period by a factor of 2 to the power 1 by n. This is the generalization. If you use, from the first step, if you use n equals to 4 equals to n, then you will reach that result also. Okay, so this was an important question, and so you will find there are options. So the correct option will be decreased by 2 to the power 1 by 4. Okay, just go through the whole procedure and pause the video if you want to note it down in your copy. So do that. Okay, okay. Now coming to another problem. Yeah, so it is a problem of the where form of R has been given, that is L square by K mu by 1 plus epsilon cos theta. You all know this equation really well. So we have been asked that if epsilon takes different values, so how the path will be, how the trajectory will look like. Okay, so okay, now this is your given equation. So I have written L square by K mu as C. Okay, now if your epsilon is 0, that means if you put epsilon 0 here, it will be R equals to C only. Okay, because 1 plus epsilon cos theta will be, epsilon is 0 means the second term will be 0 and it is only C. So R equals to C, what does it means? R equals to C means that your radius is always constant. I mean, it is not changing with time. So only a circle has this type of feature, where although it is not not looks like a circle, it is a circle. So for this case, your radius is always constant. The property of circle is that is the radius is from the center is always constant. So this will imply a trajectory that follows a circular orbit. Okay, just a second. Okay, now that is the equals to 0 case. Now equals to E means epsilon, sorry, not E, epsilon equals to 1. So then our equation, then the equation will look like R equals to C by 1 plus cos theta. Now we can consider two limiting case. Okay, that when theta equals to 0 and when theta equals to pi. Now theta equals to 0 means cos theta equals to 1, so that will give you R equals to C by 2, and theta equals to pi means cos theta equals to minus 1, so the denominator is 0 and then R will tends to infinity. So R equals to C by 2 is the R minimum and R equals to infinity is the R maximum. So this is the closest approach you can say, and this is the furthest approach. Now what type of conic section has this type of property? Surely it is a parabola. Okay, because you can see this is a parabola. So this distance will be the smallest distance, I mean closest approach you can say from the focus. So it is C by 2, and this is a open type of conic section. That means your R can go up to infinity. Okay, so as we are getting for theta equals to pi, so the two value, one is the finite value, this is this one, and the infinite value is along that open end, that is not coming back to, I mean the upper part is not coming back to the lower part. So it is not a closed orbit. As it is not a closed orbit, the particle can go up to infinity distance. Okay, so this actually shows the, I mean orbiting trajectory as a parabola. Okay, so also sir has also shown in his video that if you calculate the equation of a parabola in a polar coordinate instead of our common xy coordinate, if you go to the r and theta coordinate, you will get a equation like this. So I will ask you to go to that video where sir has calculated different types of trajectories, I mean different types of conic section in the polar coordinate. So just follow that procedure and you can find that this is the equation which you will get for a parabola. And if you write your R from this equation, it is R equals to 2a by 1 plus cos theta So this equation is exactly similar to this equation what we have taken in the past. C and 2a both are constant, but the form is r equals to a constant divided by 1 plus cos theta. If this is the form in a polar coordinate, that will show a trajectory which is actually parabola. Okay. So these are the two case, epsilon equals to 0 and epsilon equals to 1, and I will ask you to do other two case what is epsilon equals to epsilon lies in the range of 0 to 1 and greater than 1. So if you calculate I mean from that in a similar way, you can find that these two will give you ellipse and hyperbola respectively. So that I mean that is very easy to do, just do it. If you cannot do it, just let me know, then I will do it. I have not done that because two cases I have shown, and just I am asking you to do the other two cases. Okay. So I am just writing, if it is 0 to 1, then you will find a closed orbit like ellipse, and if it is greater than 1, then if you will get a hyperbola. Okay. Just do these two thing, and also try to calculate the equation of ellipse and hyperbola in the polar coordinate. Then also you can I mean compare your result with the expression which already is given in the equation. Okay. Just do this two things. Very good. Okay. Now these two problems are done. Now coming to the third problem. So this picture has been, I mean this figure has been given in your problem, and it I think the question was what will be the turning point, so like that. So this figure is the potential of a particular system. Now if the system has a total energy, I mean suppose it is there is an particle. So if that particle has an energy of E1, total energy of E1, so you can see it is very easy. I mean clearly you can see that the turning points are actually this one, Q1, Q2. So the motion for E1 can be bounded in this region, because here your kinetic energy is non-zero, because the kinetic energy plus potential energy is equals to total energy. Okay. Now in this region between Q1 and Q2, your potential energy is less than the kinetic less than the total energy. That means you have non-zero kinetic energy. So the particle can lie in that particular region. Okay, because your E is greater than potential energy in this Q1 to Q2, and it cannot go beyond Q1 and Q2, because beyond Q1, I mean in this region, your potential energy is higher than the kinetic total energy. That means E minus PE will be negative, and as you know, kinetic energy is you can write as half m r dot square. So m is positive and r dot square is also positive, so kinetic energy cannot be negative. Okay. So the particle cannot be in the region beyond Q1 as well as beyond Q2, because here also the potential energy is greater than the total energy. That implies kinetic energy is negative. That cannot be possible. That is not possible. Okay. But again, the particle can be in this Q3 to Q4 region, because of the same reason. Here the potential energy is less than the total energy, so that there is a non-negative kinetic energy. Okay. So for the energy of E1, our turning points are Q1, Q2, Q3, Q4, and the motion will be bounded within those region. I mean Q1 to, the motion will be Q1 to Q2 range. I mean how I can write it. So let us say that it will be bounded in Q1, Q2 range, where Q1 and Q2 are the lower and upper limit, as well as Q3, Q4 range. It cannot go beyond Q4, it cannot go beyond Q1 as well, and also it cannot be in the Q2, Q3 range, as the kinetic as the total energy is greater than the, as the potential energy is greater than the total energy E1. So this is the case for the E1. Now suppose you have a energy of E2. Okay, so you can see for E2 the whole region, I mean this whole region between Q0 and Q, what is this, 5, Q5, the potential energy is always less than the total energy. So this is always positive because your E is greater than PE, potential energy. That means you have a non-zero and positive kinetic energy. So the particle can be anywhere between that Q0 to Q5 range. Okay, it don't have any, I mean, region where it cannot go like that particle with energy Q1. Okay, E1. So for E2 total energy, the turning points are Q0 and Q5. Okay, and all the range, I mean between Q0 and Q5, the particle can stay in any of in all the range between that Q0 and Q5. Okay, so this is very easy thing, you have done it also, I think. Okay, now now we will go to another problem from your assignments. So here it is a, I mean it is a very interesting but a small problem, but it's a good one, that a particle is fired into an elliptical orbit in an attractive central potential of an infinitely massive object. Infinitely massive object means your, I have always said that if you have m1 and m2 and if your m1 is infinitely massive, then your reduced mass can be replaced by m2 only, the mass of the particle. That's why it is given infinitely massive object. Okay, so now let E be the total energy of the particle at the location at which it is fired. If the energy E were to be doubled, keeping the eccentricity of this part is important. So E has been doubled, but you are bound to keep your eccentricity of the orbit fixed. This is your given condition in the question. Then which of the following statement is incorrect? Okay, so we will find it. Now, as I have always told you that please try to remember this type of expression in the central force chapter, then it will be very easy to solve. So eccentricity can be written as like this expression, where E, capital E, is the energy of the particle, L is the semi-lattice rectum, or you can say L square by mk. Capital L is the angular momentum, and mk, k is actually that potential from A by R type potential, where, I mean, no, so if it is a gravitational potential, that is G mm by R. So G mm by Gm, this is actually k. So k is a constant actually, that is the numerator part of your potential, which is independent of R. The denominator gives you the dependency of R. Okay, so that k is that. Now the equation says that we have doubled our energy, but the eccentricity is same. Okay, so this is the expression of the eccentricity when we have energy E, and this is the expression of eccentricity where we have energy E equals to 2E. That's why the 4 comes instead of 2. Okay, sorry, and and the L1 and L2 are the corresponding semi-lattice rectum of that particular trajectory. Okay, so if you calculate according to question, as E1 is epsilon 1 is equals to epsilon 2, so these two are equal, and just equate them, and you will get L1 by L2 equals to 2. That means your L2 equals to L1 by 2. Now if you substitute your small l with capital L, which is the angular momentum, then you will find, just do that L2 is L1 by root 2. So L2 is actually corresponding angular momentum with which have energy 2E, and L1 is energy E. So it is the modified L2 after doubling the energy. Okay, so you can see our new angular momentum corresponding to the double energy than the previous have a so the particle which has double energy has a angular momentum which is 1 by root 2 times lower than the previous angular momentum. Okay, so here you can see it is written that angular momentum becomes root 2 times the original. That means it is saying that L2 equals to root 2 L1, but that is not correct. We are getting L2 equals to L1 by root 2, not root 2 L1, right. So this statement is the incorrect statement because the correct statement will be angular momentum becomes root 2 no. So the new original angular momentum is the root 2 times of the new angular momentum, or the new angular momentum is root 2 times less than the original angular momentum. It is not a multiplicative factor, it is the I mean 1 by root 2 is the multiplicative factor, you can say. Now if we want to do the semi major axis and semi minor axis, then your semi major axis can be written as minus k by 2e. It I have also done it in my previous videos. Just go to that video, you will find it. I have done it. So that means k is the constant. So alpha a that is the semi major axis varies as 1 by e. So if we increase the energy 2 times of the previous energy, then a will be half than the previous case. I mean semi major axis will be half than the previous case, as well as semi minor axis, which is b, is proportional to a, that will also be halved. I mean both the semi major axis and semi minor axis will be half than the previous case. So here it is written semi major axis is halved, it is correct. Semi minor axis is halved, it is also correct, but it was the wrong answer. So the wrong answer is actually your answer according to the question. So this is the incorrect part. Okay, and always try to remember all this expression. I have said repeatedly to try to remember this expression, that you can see, if you can remember this, it is so easy to calculate. Okay. Okay, so this was the things. So a varies 1 by e, b varies also as a, that is 1 by e. Okay, I think it is clear. So till now this was a very small but little interesting problem. The main part was here. Just write the expression for eccentricity and make them equal, you will get your result. Okay. Okay, now sorry, now coming to another problem. Okay, it was a nice problem. Okay, so here it has been asked to compare the circular and parabolic orbit corresponding to same angular momentum. That means your L is same. The perihelion distance, and the condition is given that the just a second, do not disturb. Yeah, and the condition is given that the perihelion distance of the parabola is alpha times the radius of the circle. It is given. Then we need to calculate the alpha. Okay, so for a particle with angular momentum L and orbiting radius r, we can write L equals to mkr, root over mkr. This part also I have done in one of my tutorials. Just go to that problem. So all these expressions are very important to solve the problem. You can do it from the first principle also, but that will take time, and to know how to do it from the first principle, I will refer to go to my older videos where I have calculated all this. Okay, so here your L is the angular momentum, m is the mass of the system, k is again the same constant which is coming from the potential energy of the system, and r is the radius. So if you write it, then your r equals to L square by mk. Okay, so this we need in our calculation. Now perihelion distance of a parabola. Perihelion distance means the closest approach of a body in a parabolic system. So that is called the perihelion distance, and that perihelion distance, I mean for a conic section you can write that r equals to L square by mk 1 plus epsilon cos theta, Now if you put your theta equals to 0, that will give you the distance of the perihelion distance of that parabola. So I have done the same thing, and also know that for parabola our another condition for eccentricity is epsilon equals to 1. So I have just put my epsilon equals to 1 and theta equals to 0 in this equation, which is, I should not write it as P, this is R, the actual equation, and by imposing those condition that theta equals to 0 and epsilon equals to 1, I am getting the perihelion distance, which I have written as Rp, that is L square by mk by 1 plus epsilon. Okay, I have put epsilon 1 in this, in the second step. Here I have put the theta equals to 0. So this is your Rp in terms of angular momentum, mass, and the constant, that is k. Now in the question it is given that the perihelion distance of the parabola, okay, so pardon me, it is I have drawn that ellipse, it is a parabola actually, okay, yeah, pardon me for that. So this is your distance of perihelion distance from the focus, okay. So that is so epsilon equals to 1 and theta equals to 0. If you put your R equation, that will give you perihelion distance. So and according to the question, that this perihelion distance is alpha times radius of the circle, okay. So this L square by 2 mk, this L square by 2 mk, this one is actually alpha times this one. I have just done that. So you can see Rp equals to alpha R, that means L square by 2 mk is alpha times L square by mk, and L square by mk, L square by mk will be cancelled out. So your alpha will be 1 by 2. So this is the value of alpha which we got from imposing the condition which has been given in our question. So you can see the value of alpha equals to 1 by 2, and it was one of the options. So that will be the correct option. Just remember this particular thing which is important. You can do it from the first principle also. I am always saying that, but it is easier if you can remember it, okay. So just do it, just calculate, just write your radius of the circle and perihelion distance of the parabola in terms of capital L square by mk. That will give you the result, okay. Okay, so I think you have understood this part. Now this is a good problem. I really like this problem. So someone asked about this problem in the last class also, okay. Okay, so what this problem says, that a rock is fired vertically upward from the surface of the earth. So it has been fired from the surface of the earth, and it reaches a maximum distance. So if it is the center, it reaches a maximum distance of alpha r, where r is the radius from the center, where r is the radius. Let v denote the speed with which the rock was fired, okay. So just focus up to this part of the question, that one thing is fired and it has been fired with the velocity v. So what we can get from this particular sentence, what information we can get, okay. So what we have done the conservation, energy conservation thing, okay. So this is the surface. Here your kinetic energy, as it has been thrown with velocity v, half mv square, and your potential energy will be g mm by r, because the radius is r. This is the r. It has been said in the question that the r is the radius of the earth, and as we are launching it from the surface, so we are at a distance of capital R from the center. So this is your total energy at the surface, and at this highest point, if I say at this point as A, so at this highest point, the the particle or the stone attains a zero velocity, right? Because at the highest position it will attain the zero velocity, and then it will start to drop in the opposite direction. So here at point A, v equals to 0, all the energy will be the potential energy, that is g mm by alpha r minus, because it has been already said that the distance is alpha r, and here g mm is coming from the gravitational force, and I have considered the capital M as the mass of the earth and small m is the mass of the stone or the object, rock, whatever it is. Okay, so that is coming from this. Now we will equate this to energy according to energy conservation. Okay, just that thing I have done in this first equation, that half mv square minus gmm by r equals to minus gmm by alpha r. Now if you calculate properly, then just do the algebraic manipulation and the I mean just take that gmm by r in capital R in the right side of the equation and calculate, you will get the v equals to this expression, which is important. So from this first sentence we got that the required velocity to attain a distance alpha r is this much. Okay, 2 alpha minus 1 by alpha r times gm, and it is under root I mean the total expression. So that is the velocity with which it has been thrown from the surface of the earth. Now come to the second line. Now what it is said? It said that now imagine that the same rock is taken to a distance beta r from the center of the earth and then fired with the same speed v as before. So now what has been done, that it has been taken to another distance beta r, and it has been fired with the same velocity v, which velocity I have just calculated. With the same velocity it has been fired, but this time another condition was v is not along the line joining the stone and the center of earth. So that means your v is not in this direction. Okay, your v is in other direction except the direction which is joining the position of the stone and the earth center. Okay, so this problem I have also given hint of that problem. You can find in my previous videos, one of my previous videos, that I have calculated what will be the velocity, what is our required velocity if we want the trajectory as a circle. That I have done, and I will ask you to follow the same procedure. And there you can see that I have used a condition that for the circle epsilon equals to 0, but for a parabolic trajectory you should use a condition that your epsilon is equals to 1, just that condition, and follow the same procedure which I have done for the circle. You will get to a condition. That condition is important for this problem, that I have not done that part, but you will get that condition if you follow the same procedure. Okay, so that condition is to get if the escape velocity of the object at distance, I mean not br, at that distance from which you are launching that stone, is ve, that means if the velocity is equals to the escape velocity of that position, then the particle will follow a parabolic path. So your v should be equals to ve at that particular position where it has been said, as in our question it has been said at beta r. So your r can be anything. Just try to derive this condition. I have done it for the circle, and I can say for the circle what I got. Just a second. My notes I have written. Oh, I am not getting it where I have written, whatever. So you can find in here. Yeah, I think so. There you can see that if it is for circle, yes. So if it is v equals to ve by root 2, then it will follow a circular path. That this part I have done. But if it is v equals to ve, then it will follow a parabolic path. Just try to derive from the same procedure which I have taken in that video. Okay, so no need of writing that. So okay, now the condition is we have to equate our escape velocity at this position with the velocity which it has been launched. So at beta r position, the escape velocity can be calculated using this expression, that half mv square, v is the escape velocity, minus gmm by beta r that is the potential energy at that position beta r, that is equals to 0. So this will give you the expression of escape velocity VE. Now just calculate V equals to VE. So here you have already calculated your V, which is this one, 12, that one. So this is that expression, and VE is this expression. Okay, just equate these two expression and you will reach to this condition. So if your 1 by alpha plus 1 by beta is equals to 1, then you will get a parabolic path for the stone which has been launched from a distance beta r with the velocity v. Okay, so this is the required condition. This was a very nice problem, and just I think this part is I mean, I have tried to make you understand what I have done. Just pause the video and go through each steps. That first one, the energy conservation, which is giving me the launching velocity capital I mean v, not capital. Then the condition which we require, that our v must be equal to escape velocity, so that we have calculated the escape velocity at the position beta r, which is this one, and we have equated that v with ve. Then our condition 1 by alpha plus 1 by beta equals to 1 comes out as the answer. Okay, just do this calculation, and you can see there was an option of this also, this one, the option 1 by alpha plus 1 by beta is equals to 1. Okay, so this is the condition for the parabolic path. Okay, now this was a very simple problem from which assignment I forgot, it may be 5 or 6. So it has been given that there is a transformation matrix, and one of the eigenvalue of the transformation matrix is given as 1 plus I by root 2. So in one of his videos, sir has already calculated, and it has sir has proved that for a transformation matrix A, we generally get 3 eigenvalues, alpha lambda 1, lambda 2, lambda 3, and one of the eigenvalues must be 1. Okay, and other two will be complex conjugate. I mean, if one is e to the power I alpha, another one is e to the power minus I alpha. This sir has already done, just go through that. So this is the property of the transformation matrix. Now 1 plus I by root 2 is given, so one complex part is given, then other will be just the complex conjugate of this, that is 1 minus I by root 2, and another one must be 1. This is important. So one eigenvalue of the 3 must be 1. So your answer will be 1 minus I by root 2 and 1. So you can see this is the answer. Right, this is a simple thing I have just included to tell you. This is the condition, that one will be 1 and other 2 will be complex conjugate to each other. Okay. Now this problem I have done in the last class, I mean just the previous class, that consider two sphere of radius r and mass m and separated by a thin massless rod, and the distance between is 2L. So what will be the moment of inertia? So that I have already done, just go through that video. So it is easy. So for a sphere I have which is rotating around this axis, it is 2,5 mr square. This also I have proved in the previous class. Now it is rotating it is the value when it is rotating around this axis. Now if we want to calculate our moment of inertia, it is I, at a distance from the center of mass A, at a distance A from the center of mass. So in that case the moment of inertia will be ms square, 2,5 mr square, which is the intrinsic inertia of the sphere, plus mass times the distance of the point from where we are measuring the moment of inertia and the center of mass. So that is the distance, and as it has two sphere, it will be just double of the I mean, it is a symmetric system. Another sphere will be this side also from the observational point. So it will 2 times of each sphere. Okay, that is 2 times 2 by 5 mr square plus ml square, because the length has been given as 2l. So half the length is actually l. So in my question, according to my question, that a is actually l. That I have done in the video. Just go through this. So this will be your answer for the zz component. That is 2 times 2 by 5 mr square plus ml square. Okay. Okay. Now, yeah. Now another problem from your 8th assignment, I think. So you have to calculate this epsilon ijk, epsilon ilm, capital Ijk, where epsilon are the LABC beta symbol. This has been taught in the very first class, or the second class, I think. So the main thing is you need just a property ILM. So this is delta JL delta IJK, it was K, sorry, delta JM delta KM minus delta JM delta KL. So this is the property of LABC beta symbol which you have to remember, and it's not a hard thing to remember because it has a pattern. Okay, so for the first delta you use the second symbol and the second symbol, the second, not a symbol, index, second index of the both LABC beta symbol, that is JL, and then the third index of the both LABC beta symbol. So J will couple with L, K will couple with M, and for the second term, it is just the opposite. So in that case, J will couple with M and K will couple with L. Okay, so this is JM KL, JL KM minus JM KL. So this is pretty easy to remember. Just use that property and operate it with IJK. So this will be the 2 term. Now delta JL is equals to 1 only when J is equals to L. If J not equals to L, then delta JL equals to 0. Okay, so to get the non-zero delta function, our J must be equals to L. So this J will be replaced by L, and also K should be equals to M. So this K can be replaced by M. So that is ILM. In a similar way, here J should be equals to M. That's why J has been written as M in the next step, and K should be equals to L. That is K is written as L in this step. So ILM minus IML. And there is another property of the inertia tensor, that is IIJ is a symmetric tensor. That means IIJ equals to IJI. If you interchange the index, that will be same. So ILM is equals to IML. That means that this is actually 0 because of the symmetric property of the inertia tensor. So you will get the result of this expression as 0. Okay. So this is the answer, 0. Well, this is very easy to get 4 points, I think. Okay, now we will do another problem from your 8th assignment as well. So here it is a quite nice problem, that's why I have done it in a extensive way. So here it is said that imagine a rock that is symmetric. So it is important that it is a symmetric, not a spherical. So we can calculate it as a symmetric top. You have already know what a symmetric top is and what a spherical top is. So it is a symmetric top, and it is thrown deep in space away from a source of force. So there is no force, and it is then observed from an inertial frame of reference in which its center of mass is at rest. That means in that inertial frame of reference, the body is in rest. Okay, that means if the body is moving with the velocity v, then the inertial frame is, v with the lap frame, then the inertial frame is also moving with the velocity with v respect to a lap frame. That's why the body will seems like stationary in that particular inertial frame. So that body don't have any motion in that inertial frame. With respect to lap frame, both have motion, but in that inertial frame it won't have any motion. And a student claims that as the rock symmetric in shape and there are no force on it, the rock can only spin and there cannot be any precession. So we have to check what actually happens in this rock. So I have used Euler dynamical equation method for this calculation. You have already learned how Euler dynamical equation comes from where Euler equation comes. So for just 1 second. Yeah, so in short I can write that n external is equals to dl dt. It is with respect to a inertial frame, and if you go to the body frame of the particular system, it is dl dt plus omega cross L. Omega is the angular velocity with which it is moving. This transformation has also been done in the last video of the of the course. So this is an n external is the external torque. Now it is explicitly given in the question that there is no external source of force. That means external torque is also 0. So your d dash L, this part is equals to 0 actually. Okay, and L can be written in terms of I omega. So it can be written only we consider the principal moment of inertia. So L is proportional to omega only when we are considering the principal axis of principal axis. Okay, so we are considering the principal axis, and omega 1, omega 2, omega 3 are the angular velocity along that principal axis. Okay, and the principal moment of inertia is I1, I2 and I3. This we have already considered. Now if we write this equation in an open form, that means with in a component by component method, then we will get this n1 n2 and n3, 3 equation corresponding to the 3 axis, and as there is no force I have written equals to 0 in the right hand side. Okay, so this is the equation which governs the motion of the symmetric top. Now the condition for a symmetric top is I1 equals to I2 not equals to I3. This we have taken. That means we have considered that I3 is along the symmetry axis, which is not equal with the other two principal moment of inertia which is perpendicular to that axis, which is I1 and I2. So this is the definition of a symmetric top. Okay. Now if we use this definition in this 3 equation, what we will get? So okay, so consider the first equation. Just divide it by I1, that is omega 1 dot minus I2 minus I3 by I1, and again from this condition I can substitute the I2 as I1. So that I have done. So in this first equation you can see it is I2 minus I3, but here it is I1 minus I3 because I have used this condition that I1 equals to I2. So omega 1 dot minus I1 minus I3 by I1, omega 2, omega 3 equals to 0, right? Now we are defining a term which is capital omega by this, that is I3 minus I1 by I1 times omega 3. So if we define this omega like this, then the equation will look like this, because this part, this omega 3 with this term is the capital omega, and omega 2 will be left in the expression. That's why capital omega times omega 2 equals to 0. Okay, this is coming from the first equation. Similarly, if you put those in the second equation, you will get like this: omega 2 dot minus capital omega 1 equals to 0, where capital omega is same as before, and as your I1 equals to I2, this term in your third equation will be 0. So that will give you just so if it is 0, this equation will give you I3 omega 3 dot equals to 0, and I3 equals to non-zero. That means omega 3 dot equals to 0, that gives omega 3 equals to constant, right? So that I have written, that omega 3 equals to constant. This 3 simplified equation from this first set of 3 equation we got. Okay, that is this one, this one and this one. This is the this is the equation for the symmetric top which governs the motion of the body. Okay. Now these two equation, let me this equation, these two equation corresponding to the first two equation, corresponding to the first two equation of the parent system, these two I want to say. So this can be calculated and you will get the solution like this: omega 1 equals to omega 0 cos capital omega t and omega 2 equals to omega 0 sin capital omega t, where omega 0 is a constant factor. We have not defined till now what the value of omega 0 or anything, so it is a constant factor. Okay, now the main point you have to understand. So the vector which can be formed by combining omega 1 a1 and omega 2 a2. So please note that in this expression there is no a3 component. Okay, so these are the two component which are, a1 cap and a2 cap are the two direction which are perpendicular to the symmetry axis of the system. Okay, this is important. So now suppose your body is like this and it is your a3. Okay, so this direction is your a3 cap. Then your a1 and a2 will be perpendicular to that a3, right? So I have done that in a way that a1 and a2 are perpendicular to a3, and omega 1 a1 plus omega 2 a2 vector, that will be the resultant of these two vector, which is this vector. Okay, so you can understand that it is a resultant of a2 cap and a1 cap, so it will be somewhere between a2 cap and a1 cap. Okay, so this is that vector omega 1 a1 plus omega 2 a2, this one. Now this is also perpendicular to a3 axis and it has a magnitude of omega 0, because the magnitude of this vector is omega 1 square plus omega 2 square, that is omega 0 from these two equation. So the value is omega 0 and direction is shown in the figure. Now what it is actually saying that now the total omega, which is this one, which is the combination of a1, a2 and a3, both the three direction, that is this. So you can see that in the picture, this is that vector omega, which is omega 1 a1 plus omega 2 a2 omega 3 a3. Okay, so and it is clear that in figure it is making some angle alpha b with the symmetry axis a3 cap. Okay, so that means it can precess around that symmetry axis. So precession means okay, just a second. Yeah, so if this is your a3 axis and if it is your omega, so this omega can precess around your symmetry axis like this. Okay, so this can move like this. It is actually called the precession. So and the angle is alpha b, so you can calculate the alpha b also, which will be just the tan inverse of omega 0 by omega 3 if you calculate it. Okay, so but the important thing is that your omega, which is the angular velocity of the system, that is making an angle with the symmetry axis and it has a angular velocity of capital omega. So that I have written in this sentence, so read it carefully, that this omega is directed along the instantaneous axis and has a constant magnitude. Okay, why constant magnitude? Because your omega 3 is constant. Already we have seen that our omega 3 is constant, and the value of omega 1 a1 plus omega 2 a2, that is omega 0, it is also a constant. So these two part combiningly will give you a constant term, and omega 3 is itself constant. So the magnitude, that is omega 1 square plus omega 2 square plus omega 3 square under root, that will be also a constant, which is the magnitude of omega. So that is a constant magnitude and precess uniformly relative to the symmetry axis. Okay. So why uniformly? Because our omega is constant, there is no, I mean the capital omega, there is no time dependence is capital omega, it is just I3 minus I1 by I1. Okay. So it is uniformly precessing with the constant angular velocity omega and constant amplitude omega 0. Okay. So this tells that our system, although it is free of any torque and any external force, still it can precess around its symmetry axis. So the statement which has been done by the student in the question that it can only spin and there cannot be any precession, this is not the correct one, because there can be precession although there is no force acting on the system. Okay. So this is important thing and you have to understand it well, that without force it can precess, but if you want nutation of the body, then you need a external force which is acting on the body. That problem has also been solved in the last class of the course. So you can see that here there sir have considered the heavy symmetric top, I think heavy symmetric top was it, whatever, heavy symmetrical top, and there the nutation has there he have considered the potential due to gravity also, which is acting as an external force, and due to that there will be nutation as well as with the precession. But here only the precession can happen, no nutation is there. Okay. And the angle is tan inverse omega 0 by omega 3. So this is important thing, and it is coming from only solving the Euler equation, dynamical equation with the proper condition for the symmetric top. So just do it and just go through it once and try to think about it and try to understand this figure which is important. The pictorial representation is important for this problem, how the omega is making an angle with the A3 cap, this is important to understand. So I think if you once go through by yourself with this problem, then you can understand it in a better. So okay, so all these problems from different, I mean assignment from 5th to 8, I mean I have covered the 5th to 8 assignment, some problems of 5th to 8 assignment that has been done in this I mean in this video. So please go through those problems, and if you have any, if you are facing any difficulty with other problems also, just let me know in my email ID. Just let me send me the number of problem and number of assignment to my email ID, and I will try to solve those also in the next class. Okay. So I think this will help you to solve those assignments if you have not done it, and in your exam also. So any question? I mean some deep is here. Okay. And if you have any other question also, you can mail me, no problem. Solve these things. Yeah, most of the difficult problems, I mean not so difficult, but little tricky, I will say, that I have been covered in this video. Okay. Okay, then I will end this today and we will meet in the next week. Okay. Then bye and thank you.